Namaste and welcome back to yet another lecture on linear algebra through geometry. In the last lecture we were looking at this transformation, say 2 by 2, which was taking a 2 component vector giving me another 2 component vector, right. This is what we were looking at, and we said that okay, suppose you have this transformation which is like A11, A12, A21, A22 and X1, X2 is giving me, let us say, B1, B2. So, we ended the last lecture with the question that is it possible to have a vector, say u, a vector u which is not equal to the 0 vector such that a u is equal to lambda u. We asked this question and then we wound up the last class. In today's class we will basically look at the answer to this question, and that is exactly where we are heading towards the ideas of eigenvalues and eigenvectors. So, this class is on eigenvalues and eigenvectors. Now, let us get into the details of what we are trying to do here. So, suppose I consider my matrix A as a system. Let us take this example. Let us consider this matrix, say 2 1 1 2, right. This is what we have. This is going to be the system that I am going to have. Assume that A is equal to 2 1 1 2, right. Now, this matrix A is going to act on a 2 component vector x1 x2, or 2 component vector x whose components are x1 and x2, to give a vector B which is again a 2 component vector whose components are B1 and B2. Now, what I am going to do is I am just going to take some examples of x vectors and see what are the B vectors that I am going to get upon action by this matrix A or this system A. So, I am going to look at some examples. The first example that I am going to do is I am going to look at x vector to be equal to the 1 0 vector. 1 0 vector more so because that is a vector that is along the x1 direction. So, any vector along the x1 direction can be written as x1 scalar x1 times the vector 1 0, and any vector along the E2 axis can be written as x2 into 0 1. So, I am going to look at x1 into 1 0. What does this transformation to 1 do to 1 0? We see that the resultant of this is the B vector which is given by 2 1. Now, let me take this vector x vector which is equal to 0 1, and that is going to give me this B vector which is nothing but 1 2. What am I looking at? I am just looking at Ax equal to B. So, how do we do this? This is basically saying Ax equal to B, where x's are the vectors x are all on the left hand side and the vectors B are all on the right hand side. So, that is what I am trying to do here. Now, then I have this third guy which let me take x vector to be equal to minus 1, let us say 2, minus 1 2. So, what does this do to minus 1 2? So, I am going to have 2 1 1 2 into minus 1 2. So, that is going to take me to this 2 into minus 1 is minus 2 plus 1 into 2 is 0. The 1 into minus 1 is minus 1 plus 2 into 2 is 4. So, 4 minus 1 is 3. So, I am going to go to 3 0 3. So, this is going to give me B is equal to 0 3. The fourth vector that I am going to look at is basically this input, where I am going to take x vector to be equal to 1 1, and I see that the output vector is basically b is equal to 3 3, right. And the fourth vector that I am going to do is basically this guy, which is x vector is equal to 1 minus 1, and that is going to give me another b vector which is 1 minus 1. Now, what does this all mean? We will get to understand what this all means when we pictorially see this. When we see this pictorially, we get the following things. So, let me draw the axis, say E1 and E1 E2. Let us mark all the points. So 0 1 2 3 4 5 6 1 2 3 4 5 minus 1 minus 2 minus 3 minus 5 minus 1 minus 2 minus 3 minus 4 and so on. Now, the first vector that we took in the previous in the example was 1 0 vector, and 1 0 vector was along this direction. Let me take a okay. The vector 1 0 was here, and that 1 0 vector upon the action of 2 1 1 2 went here, right. That means the matrix A acted upon this vector 1 0 to give me another vector which is 2 1. Similarly, I had this vector 0 1 which went to 1 2. So, I have this 0 1 vector. 0 1 vector was along this direction. This is the 0 1 vector, and that got thrown to 1 2, right. And the third vector that we looked at was minus 1 2 which went to 0 3. Let us look at minus 1 2. Minus 1 2 was basically this vector, and that went to 0 3. 0 3 is along this direction. This is 0 3. Then we had this vector which was 1 1. 1 1 vector was here. It went to 3 3, which is here, and last we took this last example which was 1 minus 1. 1 minus 1 was this vector, and 1 minus 1 upon action by 2 1 1 2 gave me 1 minus 1 itself. Now, what is interesting here is, if you look at all those vectors, vector pairs that I have drawn here other than the green one and this guy, you see that the input direction was something and the output direction was something else. In a sense, this is like this is like cricketer playing shots around the ground, but there are times where the cricketer is going to play a shot which is straight drive, or probably the Merlier shot, that where he places the ball in the same direction but behind the stumps, right. So, there are, if you look at this red color one or the purple color one or the blue paired arrows, these are all vectors which have these are all the input vectors was in some direction, and the resultant, the transformed vector, was in different direction. However, if you look at the vector which was in the green direction, or let us say the vector 1 1, 1 1 vector was transformed to the vector 3 3, and the vector 1 minus 1 got transformed to 1 minus 1 itself. That means we have certain vectors for the transformation A such that they do not undergo a direction change, instead they just go through scaling, right. In this case what had happened is if I take this matrix 2 1 1 2 this transformation and we have this 1 1 vector, this gave me the vector 3 3 where 3 3 vector was nothing but the scalar multiple of 1 1 itself. Similarly, if you take this vector 1 minus 1 2 1 1 2 into 1 minus 1, that gave me 1 minus 1 itself, which was essentially 1 time 1 minus 1, right. That means we see that in these two cases alone the direction of the resulting vector, the transformed vector, and the direction of the input vectors, these are the same, except that the effect of the matrix A or the transformation A on the vector 1 1 or 1 minus 1 was just to scale the vector and not do any kind of direction change. So, we are going to call such vectors as the eigenvectors, and the scaling factor that is associated with these vectors as the eigenvalues. So, let us write the definition. A vector u is called an eigenvector to the matrix A if AU is equal to lambda u for some scalar lambda and lambda is called the eigenvalue. In fact, we say that u is the eigenvector associated with the eigenvalue lambda. Eigenvector associated with the eigenvalue lambda. Yeah, that is associated with the eigenvalue lambda. Now, the question is, how do we find these eigenvectors, how do we find the eigenvalues, what is the use of these eigenvalue and eigenvectors, where do we use this applications? These are things which we will actually look at it at a later point of time, but right now what we will do is we will try to find out a way to get the values of eigenvalues and eigenvectors. Okay. So, that is what we are going to do. So, what is it that is given to us? We say that Ax or let us say Au is equal to lambda u, right. Now, lambda is a scalar, that means we have A into u1 u2 is equal to say some scalar lambda into u1 u2, right, lambda scalar, right. Okay. Now, how do we find the values of lambda and how do we find u? So, the question is, how do we find lambda and how do we find u? So, that is a question. So, how are we going to do it? So, it is very easy. Now, what we do is we look at this, we have Au is equal to lambda u. A is basically this matrix, we have A11, A12, A21, A22, this is the matrix that we have. So, what am I going to do? I am going to take this matrix A into u, I am going to say this is equal to lambda times I times u, lambda into I times u, where I is the 2 by 2 identity matrix 1 0 0 1. That is the identity transformation or the identity matrix that we have. So, which implies I can bring this to lambda I u to the left hand side. So, I am going to get A minus lambda I times u gives me the 0 vector. This is what we are going to have, it is equal to the 0 vector. Now, if you look at this expression carefully, let me call this as equation 1. If you look at equation 1 carefully, this A minus lambda I is yet another 2 by 2 system, which is going to be like this: A11 minus lambda, A12, A21 and A22 minus lambda, and what we want this into U1 U2 is equal to 0 0, right. This is what we want. So, this is basically equal to say some other system Bu is equal to 0. That means you are looking for the solution to the homogeneous system of equation, which is nothing but A minus lambda I into u is equal to 0. So, what do we want? U vector is basically the solution to the homogeneous system let me put it this way: u is equal to u1 u2 is the solution to the homogeneous system A minus lambda I times u is equal to 0. The right hand side is the 0 vector. Now, we want this u to be non-zero vector. Remember, when we defined the eigenvector, we said that here again we said that is it possible to have a vector u not equal to 0. That means the vector that we are looking for, u, must be a non-zero vector. So, we want a non-zero solution to A minus lambda I into u is equal to 0. That means you are looking for a non-trivial solution to A minus lambda I is equal to into u is equal to 0, non-trivial solution u to A minus lambda I u is equal to 0. This is what we want. We already have seen before that if we want a 2 by 2 system of homogeneous equations or homogeneous system of equations to have a non-trivial solution, that corresponds to saying that the determinant of the matrix A is going to be 0. If the determinant of the matrix is 0, we are going to have either a non-trivial, we are going to have a non-trivial solution to the homogeneous system of equations. So, let us write that. Recall that if determinant of A 2 cross 2 is equal to 0, then the homogeneous system of equations HSE, let me write that as HSE, Ax is equal to 0 has non-trivial solutions. Now, what does that mean? That simply means here again, if you look at this, we want A minus lambda I times u is equal to 0. This is what we want. We wanted our u to be not equal to the 0 vector, and therefore, if that is the case, if you look at this equivalently, we are going to say that determinant of A minus lambda I times u, determinant of A minus lambda I is equal to 0. That means the matrix A minus lambda I is basically a singular matrix. The determinant of this must be equal to 0, and this is exactly what we refer to as the characteristic equation of A. Characteristic equation of A, the matrix A, right? Determinant of A minus lambda I is equal to 0, characteristic equation of A. So, if we take our 2 by 2 case, we had A11 minus lambda, A12, A21, A22 minus lambda. This is what we had. This is the matrix A minus lambda I. We want the determinant of this is equal to 0. we want the determinant of this to be equal to 0, which corresponds to a11 minus lambda into a22 minus lambda minus a12 a21 is equal to 0. We see that it is a quadratic equation that we have lambda square minus lambda into a11 plus a22 plus a11 a22 minus a21 a12 is equal to 0. This is what we have. So, the roots of this equation, so the roots of, and this is basically the characteristic equation. So, the roots of the characteristic equation gives the eigenvalues. These are the eigenvalues, the scalars, eigenvalues. It is interesting to see that if you have a quadratic equation, the coefficient of lambda is basically the sum of roots, and the constant term that you are going to have is going to be the product of roots. In this case, the product of the roots is basically the constant term is this corresponds to determinant of A, and this corresponds to sum of diagonal elements, which is basically called the trace. Sum of diagonals, which is called trace. So, what we are going to say is, we are going to make a statement here to say that product of eigenvalues is equal to determinant of A, eigenvalues of A, and sum of eigenvalues is equal to eigenvalues of A is equal to trace of A. So, what we have now, we will have two roots here, namely lambda 1 and lambda 2 are the two roots here, or two roots of the characteristic equation of A 2 by 2. So, lambda 1 is one eigenvalue and lambda 2 is the second eigenvalue, another eigenvalue. Now, what we need to do is we substitute this value to find out the values, to find out the eigenvectors. We get A minus lambda 1 times I into, let us say, u is equal to the 0 vector. This is one equation. The second equation is A minus lambda 2 I into, let us say, v is equal to 0 vector. So, u corresponds to the eigenvector associated with lambda 1, eigenvector associated with lambda 1, and v is the eigenvector, associated with lambda 2, right. So, we can solve the homogeneous system of equations. These two are homogeneous system of equations which can be solved to find out the value of u and v, right. So, now let us take our simple example where we had 2 1 1 2 and we wanted to look at, let us say, x1, let us say, okay. So, we wanted to find out the eigenvalues of this matrix A is equal to 2 1 1 2. So, we can do the characteristic equation here. So, the characteristic equation is determinant of 2 minus lambda 1 1 2 minus lambda is equal to 0. So, I am going to have 2 minus lambda the whole square minus 1 is equal to 0. We are going to get lambda square minus 4 lambda plus 3 is equal to 0. We are going to have lambda is equal to 3 and lambda is equal to 1, lambda 1 is equal to 3, lambda 2 is equal to 1. This is exactly what we had seen before in this. So, we had, if you look at here, we have seen this here, we had 3 and 1, and that is exactly what we see here. Lambda 1 is equal to 3, lambda 2 is equal to 1. You can easily verify that the product lambda 1 into lambda 2 is equal to 3 into 1, which is 3, which is nothing but determinant of 2 1 1 2, and lambda 1 plus lambda 2 is basically 3 plus 1, which is equal to 4, which is nothing but sum of diagonal elements of A, sum of diag. Sum of diagonal elements of A. Now we can solve the system of equations to find out the eigenvectors. We have, for lambda 1 is equal to 3, we have 2 minus 3, 1 1 2 minus 3, let us say u1 u2 is equal to 0 0. We have minus u1 plus u2 is equal to 0. You have u1 minus u1 minus u2 is equal to 0, which means I am going to get u1 is equal to u2. So the vector, the eigenvector is basically u1 u2, which is same as, basically since u1 is equal to u2, I am going to write it as u1 comma u1, which I will write this as u1 into 1 comma 1. That means you can put any scalar here, that multiple, scalar multiple of 1 1, that means 1 1 is basically the eigenvector that we are going to have, right. So the eigenvector is 1 1, corresponding to lambda 1 is equal to 3. Similarly, we can find for lambda 2 is equal to 1, the eigenvector is 1 minus 1. Yeah. Okay. Now there are a few questions that we want to answer here. So we know how to find out the eigenvalues, we know how to find the eigenvectors. Now the questions that we have is, number 1, is it always possible? Is it always that for a 2 by 2 matrix A, we get real eigenvalues? Right? This is the first question that we want to answer. It is a very important question, because we see that the characteristic equation of a 2 by 2 matrix, the characteristic equation is basically, let us say, lambda square minus lambda into some trace plus determinant of A is equal to 0. Now this is a quadratic equation where both roots, so quadratic equation both roots can be complex, that means the roots will appear as complex conjugate pairs, in which case we will not have eigenvalues to be real at all. So which means no real eigenvalues. No real eigenvalues implies that the eigenvectors are also not real. So no real eigenvalues, and therefore no real eigenvectors, no real eigenvectors. And now what does that mean? That simply means there is no such transformations, there is no fixed direction. That means any vector that you give, this transformation is going to throw it to a different direction. Where do we see an example? The best example that we look at is basically the matrix R theta, which basically rotates every vector by an angle theta. Of course, theta you could say theta 360, theta 0, all those things would correspond to the same direction. So, what we do is we will take a simple example in this case, where I am going to take this rotation by 90 degrees. I am going to look at r 90 degrees. So, we remember that r theta was cos theta, sin theta, minus sin theta, cos theta. So, if you look at r theta now, r theta is cos 90, theta is 90. So, let me mark this as 90 degrees, theta is 90 degrees. So, I am going to have 0, 1, minus 1, 0. Now, if you look at the characteristic equation for this, characteristic equation will be determinant of 0 minus lambda minus 1, 1, 0 minus lambda is equal to 0. We have lambda squared plus 1 is equal to 0, which implies lambda square is equal to minus 1 and lambda is equal to plus or minus I. That means this does not have a fixed rotation, a fixed direction at all. That means this rotation matrix will not have real eigen values and hence real eigenvectors. So, the second question that we ask is, what happens if the roots are repeated, the roots of characteristic equation of A 2 by 2 are repeated? What does that mean? We have this characteristic equation, which is lambda square minus lambda into sum of roots, means sum of diagonal plus determinant of A is equal to 0. In this case, we are going to have lambda 1 is equal to lambda 2 is equal to lambda itself. Now, if this happens in 2D, if this happens, just a minute. So, if this happens, if eigenvalues are repeated for a 2 by 2 matrix A, we have only one eigenvector, that means we have only one fixed direction, one fixed direction. Now, where do we see this? We look at this example where I have A to be equal to 1 1 0 1. Now, characteristic equation in this case is determinant of 1 minus lambda 1 0 1 minus lambda is equal to 0. That means I am going to have 1 minus lambda the whole squared is equal to 0, which means lambda is equal to 1 twice. In this case, we will just get one eigenvector, only one eigenvector. So, because the roots are repeated, we just, in this case especially A 2 by 2, in a 2 by 2 case, if the eigenvalues are repeated, we just get one eigenvector, which we can very clearly figure out. So, let us figure out what are the, let us find out what is the eigenvector corresponding to lambda is equal to 1. So, we wanted A minus lambda I times u is equal to 0. So, we have 1 minus 1 0 1 1 minus 1 u1 u2 is equal to 0 0. Let me write this. So, we get 1 minus 1 was 0, 1 minus 1 was 0, this one was there and that was 0 into u1 u2 is equal to 0 0. Excuse me. So, here we see that the first equation tells me that 0 u1 plus u2 is equal to 0, which implies u2 is definitely 0, and since it says 0 u1 is equal to 0, u1 can take any value, u1 can take any value. Any value, right. Therefore, the eigenvector is u1 u2 is equal to, let us say some k comma 0, which is k into 1 0 for k real. That is the only direction that we have. And what is this matrix that we looked at? This is basically the shear matrix we have. This is the shear matrix that we had, which has only one direction, or that means only one eigen direction. In all other cases, when you have two distinct eigenvalues, you will have two distinct eigenvectors. You will have two different two directions, basically two eigenvectors you will have. And what is interesting is there are many applications of eigenvalues and eigenvectors. One is to compute the powers of the matrix A. All these things we will actually look at it when we do the when we go to the vector space, and where we look at invariant vector spaces and stuff. There we will look at this diagonalization of a matrix and things, but the most important thing that we want to emphasize here is the fact that for a transformation for a transformation, let us say a 2 by 2 transformation A, we can have two fixed directions. You can have only one fixed direction, or you do not have any fixed direction at all. That means you may have two eigenvectors, you may have only one eigenvector, or you do not have real eigenvector at all. So, that is the conclusion that we have, and it is in fact more interesting. We will just look at this particular matrix which we started working with 2 1 1 2, where we figured out that the eigenvalues are lambda 1 is equal to 3, and the corresponding eigenvector was 1 1, and lambda 2 is equal to 1, the corresponding eigenvector was 1 minus 1. Now, it is interesting to see that 1 1 dot product with 1 minus 1 gives me 0, which means this implies there is something that is happening, a very important property which we will just mention here, but we will prove it at a later stage, where we say that if A is a real symmetric matrix, let me write this as A 2 by 2 is a real symmetric matrix with distinct eigenvalues, the eigenvectors corresponding to them, I will write this as the corresponding eigenvectors, the corresponding eigenvectors are orthogonal to each other. Right. So, that is a very interesting property that we have. If you have a 2 by 2 real symmetric matrix, now later we can generalize it to n by n. I mean, you can look at a n by n matrix. If it is a real symmetric matrix with distinct eigenvalues, then the corresponding eigenvectors will be orthogonal to each other. That is a very interesting property of real symmetric matrices that with distinct eigenvalues. And we will also see that the eigenvectors would turn out to be a basis. We will see the idea of basis, then vector spaces, dimension basis, and all those things maybe a couple of modules later. As of now, what we have seen is that we have looked at a lot of things in 2 dimension. We looked at the ideas of vectors and points, combining vectors, then we looked at transformations on vectors, we looked at solving system of equations. We tried to look at the system of equations from the column perspective. Then we said that we talked about unique solution, no solution and infinitely many solution cases, which we looked at again from the column picture, and then we looked at the idea of transformations which result in just scaling. That means suppose you have a matrix A and you have vectors which just get scaled by the matrix by the transformation. The direction does not change, we call them as the eigenvectors, and we said that the scaling factor is called the eigenvalue, and we looked at for a 2 by 2 matrix you may have 2 eigendirections, or you may have only one eigenvector, or you may not have a real eigenvector at all. So these are things that we have seen, and at this point of time we have almost covered everything that is need to be covered as far as 2 by 2 systems is concerned. From the next module onwards we will get into the idea of 3 dimension, we will look at vectors in 3D, we will look at interpreting the ideas of determinant of a 3 by 3 matrix, we will look at what is it to say just 2 linearly independent vectors in 3D, what happens, we will look at the new idea of cross product. These are the topics that we will be looking at in the next module. Thank you.